Okay, so this is section 16.3, the fundamental theorem for line integrals. So, as you can expect, with a name like fundamental theorem for line integrals, it's probably pretty important. Not as important as when we did the fundamental theorem of calculus, but it all relates. So, what our goal is for this section is we're going to be able to evaluate integrals of the gradient using the fundamental theorem for line integrals, or the fundamental theorem of calculus for line integrals, and also talk about this concept which is called conservative. So we're actually going to do this a little bit backwards. I usually like to give you guys all of the reasoning behind everything, and then we do examples. We're actually going to go through a couple of problems first without the reasoning, and then I'll go into the reasoning. All right, and this will probably be, I'm hoping, just 2 videos. Let's see how that goes. So the first problem says, determine whether or not capital F, which is going to be our vector field, is a conservative vector field. Well, we haven't talked about what the idea of conservative is, so for right now, we're going to go ahead and put a line through that. We will come back to that, but for right now, you don't have to put a line through yours, but I'm putting a line through mine right now, because we really haven't dealt with that yet. And then if it is, again, if it is, we don't know about that yet, find a function lowercase f such that capital F is the gradient of f. All right, so what does all that mean? So let's look at our capital F, because they gave that to us. So we've got some vector field defined over xy. So it's 6x plus 5y I plus 5x plus 4y j. So it's a 2-dimensional vector field. So our force vector, let's do this in green. Our force vector is defined as 6x plus 5y, 5x plus 4y. What it's saying is that that force, that capital F, is defined to be the gradient of f. That is equivalent to the gradient of f. Well, the gradient, if you remember, were the partials. So the gradient is the partial with respect to x and the partial with respect to y. What it's asking us to do is to find f, lowercase f, I should say. They want us to find what is the original function this gradient would have come from. That's the general concept here. So what you should hopefully be able to see is that this first component right here, if this capital F is the gradient of lowercase f, then that first component, 6x plus 5y, has to be the partial with respect to x. So we're going to write it like that. The partial with respect to x is 6x plus 5y. But what we're trying to do is get the original function. Well, if we've taken a derivative with respect to x, if we take the antiderivative of that with respect to x, we should then get back to the original. So if I take the antiderivative with respect to x, since f sub x was the derivative with respect to x, so let's see. Antiderivative with respect to x, that's going to be x squared dividing by 2, so we get 3x squared. And then the antiderivative of the 5y part is just going to be 5yx, or 5xy in this case. Plus, because there's no bounds here, there would be plus some constant c. But in this case, c doesn't have to just be a constant. C could be any function of y. So the original f is going to be 3x squared plus 5xy plus, again, any function of y, and we're going to call it g of y. Because if this was, and you don't have to write this part, if this was 7y squared right there, then the derivative of 3x squared, 5xy, and 7y squared with respect to x, the 7y squared part is just going to go to 0. And the 5xy part would go to 5y, and then the 3x squared part would go to 6x. So we would get the partial. So again, you don't need to write this part right down here because that's not really what it is. I was just throwing that out there as an example. So any function of y. All right, well, we would need to figure out what that is. Well, we have another piece to this that we can utilize. We know that this is supposed to be the partial with respect to y. So let's write that. The partial with respect to y is given to us as 5x plus 4y. If I want to find the partial with respect to y based upon this one, so the partial with respect to y based upon the original function f, well, that just means take the partial derivative with respect to y. Well, the 3x squared goes away because there's no y's in it. The second one is going to give us 5x, and the last piece is going to give us g prime of y. Well, hopefully what you can see is that these two things both represent the partial with respect to y. Since they are both the partial with respect to y, I can kind of equal those things to each other and figure out the missing piece. Well, I'm not really going to write them out as equal to each other, but hopefully you can see that the 5x's match up. So then that means that 4y has to equal g prime of y. So g prime of y equals 4y. Well, I'm not looking for g prime of y. I ultimately need to find g of y. So that's the antiderivative of g prime of y. And again, this is with respect to y, so we can take the antiderivative. Antiderivative with respect to y here is going to be 2y squared plus some constant. Now, you can use c. For whatever reason, the book that I use uses k in this case. It's just another constant. Technically, you could use whatever letter you want to let represent a constant, but they use k, so I'm going to stick with k. So that is g of y. This is going to get plugged in right there. So our original function, f of xy, is then going to be 3x squared plus 5xy plus our g of y, which we just found to be 2y squared plus k. That is the original function that they were asking us to find in this particular problem. That is lowercase f. Right there, try and squeeze that all in there. All right, so hopefully that makes sense. Now, the important thing is here is that they are defining capital F, or your vector field force function, as the gradient of lowercase f. And if that's the case, then we found a way to find the actual function lowercase f. All right, let's look at a second problem. Same general idea. Again, we'll come back to determining about the conservative stuff because we haven't dealt with any of that yet. So they're defining capital F as the gradient of lowercase f. So let's go ahead and write out our gradient function. The gradient of lowercase f is going to be 2x cosine y minus y cosine x. That's the x component. Then the y component is negative x squared sine y minus sine x. So again, that first piece is going to be your f sub x, your partial with respect to x. So the partial with respect to x is going to be 2x cosine y minus y cosine x. But ultimately, we're trying to get back to f. So that means we need to take an antiderivative with respect to x. So remember, all the y pieces, treat them like constants here. So the antiderivative with respect to x is going to give us x squared cosine y. Antiderivative of the cosine of x is going, or the negative of cosine of x is going to be negative sine of x. So it's going to be negative y sine of x plus some function of y. Okay, so now we're going to go ahead to kind of finish off this puzzle. We're going to say, okay, well, I know that the partial with respect to y, based upon the fact that the gradient was given to us, is negative x squared sine of y minus sine of x. But I need to figure out what the derivative with respect to y is of the original function so that I can kind of match it up with the gradient piece that was given to us. So let's take the derivative here with the orange arrow from the original function with respect to y. So the derivative of this first piece with respect to y is going to be negative x squared sine y, negative x squared sine y, whoops, forgot to put my f sub y there. Then the derivative of this piece with respect to y is just going to eliminate the y, so it's going to be minus sine of x. And then the derivative of this piece with respect to y is plus g prime of y. So then again, what you're going to understand is that both of these represent the partial with respect to y. Well, in this case, both pieces that we have that are there match up, which means that g prime of y has to equal what's left over. Well, that's 0. So we've got that g prime of y equals 0. But again, we're not looking for g prime, we're looking for g. So that just means if I take the antiderivative with respect to y, well, the antiderivative of 0 is just some constant. Okay. So now I've got a g of y. So the original function f is going to be x squared cosine y minus y sine of x plus k. And there you have it. So obviously, like I said, we've done a couple of examples, and I think you'll be able to work through those examples pretty easily as far as being able to do it. But what should come up is the question of why. All right, and to talk about why, let's go back and recall, this is all the way back to Calc ABBC, the fundamental theorem of calculus. Technically, this is fundamental theorem part 2, which says the integral from a to b of some kind of a function's derivative dx. Well, if you were to take the integral of a derivative, I don't like to use the word cancel out, but they undo each other basically. So if I take the integral of a derivative, we're going to get back to the original function, and we would evaluate that from a to b, which is going to be f of b minus f of a. That was the fundamental theorem part 2 of fundamental theorem part 2, back from ABBC. All right, so how is that going to relate to anything that we're doing now? Well, if we want to find the integral, a line integral of, and again, the way your book writes it is f dot dr. I'm going to write it out a little bit better than that because I like to see the actual derivative there. So it's going to be the integral from a to b of our force, but our force has to be parameterized. So we're going to say the force of r of t dotted with, remember that dr is a derivative, so it is r prime of t dt. Okay. So if this is the case, and we let capital F equal the gradient of lowercase f, because if this doesn't, if this is not the case, then none of this actually matters, and none of this works. But capital F Your vector field force has to be the gradient of F. If that's the case, then we're going to go ahead and substitute integral from a to b. Instead of writing the f of r of t, we're going to call that the gradient of f dotted with r prime of t dt. Well, so if we remember correctly, and we've just done a couple, so hopefully we do, the gradient is the partials. So if I write that as the partials as a vector, it would be the partial of x with respect to t, the partial of y with respect to t, and then if it's three-dimensional, the partial of z with respect to t, dotted with r prime of t. R prime of t are the actual derivatives, dx dt, dy dt, dz dt. So that's going to be dx dt, and these are fulls, dy dt, dz dt, dt at the end. And if you remember how a dot product works, remember we multiply each of the corresponding components and then we add them together. So what we're going to get here is the integral from a to b of, let's see, the partial with respect to x, sorry, the partial of x with respect to t times the full dx dt plus the partial of y with respect to t times the full of y dt plus the partial with respect, so the partial of z with respect to t times the full dz dt. That whole thing dt. Now this is going to go back a long way, and seems like it's been forever now. If you remember correctly, all of this is basically the chain rule. It's exactly what this is. That is the definition of the chain rule here in 3 dimensions. Okay, that's not absolutely necessary that you remember that, but that's exactly what it is. So ultimately, what this is saying is that we are taking an integral from a to b of some kind of a derivative, so d of dt, of a function of x, y, and z dt. And you might ask yourself, well, how does that actually work? Remember that the function f of x, y, and z, where x, y, and z are all functions of t, so that's where the chain rule applies. You would take the derivative of x, y, and z, multiplying each one by its derivative with respect to t, because each one, x, y, and z, are functions of t. And if this is the case, well, this goes all the way back up to the top with the fundamental theorem of calculus. I am taking the integral of a derivative. The integral of a derivative, which just says I'm going to find the antiderivative, which in this case is just going to be our capital F of x, y, z, evaluated at my endpoints, a and b. Now, granted, this capital F of x, y, z here is going to end up being functions of t. So because of that, a and b are also going to have to be values of t, but we'll talk about that when we get to it. So here is the ultimate, I guess, the ultimate definition for us. So the fundamental theorem of calculus for line integrals. If we are trying to find the line integral of f dot dr, and we are told that capital F is the gradient of lowercase f, then the line integral of f dot dr is the same thing as the antiderivative of f of xyz evaluated at the endpoints. And whoops, I think I made a slight notational mistake. That should be lowercase f. Yeah. Not to be confused with what's in green written above, because those are slightly different things. That should be lowercase f right there. Okay. All right, so let's go ahead and do, you know what? No, I think I'm going to stop there. This may end up being 3 videos, so this one's gotten to be a little bit long. So let's just stop that one right there. We'll come back and do some examples, and then we'll see if we have to do a 3rd video.